Hi everyone, today we're doing our last section of notes for chapter 3, and this is on arguments and Euler diagrams. First, we're going to draw an Euler diagram for each of the quantified statements. We have all A are B, so what this means is that we have a circle for group A, and because all of A are also B, it means our group B is going to be completely around group A. Next, we have no A are B. So I have a group A and a group B, and because none of them are in common, they are completely separate circles. For some A are B, I have a circle for group A and a circle for group B. And I know some A are also in B, so we're talking about the ones that are right here in the overlap section. For some A are not B, I have a circle for group A, another circle for group B, and I know that some A are not in B, so I'm talking about ones over here that are not in the overlap portion. Euler diagrams and arguments. Make an Euler diagram for the first premise, then you make an Euler diagram for the second premise on top of the one for the first premise. So what this looks like is we're going to have our premise 1, then our premise 2. Okay, then we're going to determine if the argument is valid if and only if every possible diagram illustrates the conclusion of the argument. If there is even one possible diagram that contradicts the conclusion, this indicates the conclusion is not true in every case, so the argument is invalid. So we put these together. Here's our conclusion. And so just some extra notes to put on here. Our premise 1 and premise 2, these have to be true. Okay, that's what we're given in the problem. Then our conclusion, we are basically trying to prove this false. Okay, we're trying to find the counterexample to prove the conclusion false or invalid. So the goal of this procedure is to produce, if possible, a diagram that does not illustrate the argument's conclusion. If possible, this serves as a counterexample to the argument's conclusion, and the argument is immediately declared invalid. Okay, so again, here it says use Euler diagrams to determine whether the following argument is valid or invalid. Again, our goal is to see if we can show a counterexample. You will be able to draw a valid argument for any of these. The goal is to see if you can show a counterexample to show that the argument is invalid. So here's our first one. All U.S. voters must register. All people who register must be U.S. citizens. Therefore, all U.S. voters are U.S. citizens. So let's try and draw this. All U.S. voters must register. So if all voters must register, that means the voters circle has to be inside of the circle of people who register. Okay, so that one's true. All people who register must be U.S. citizens. So now I need a circle for U.S. citizens that goes around those that register, because it says all people who register must be U.S. citizens. Okay. Now, because both of these had all, this is the only way we could draw this picture. Therefore, all U.S. voters are U.S. citizens. And here we see all of our voters are inside U.S. citizens. There's no other way we can draw this. So this is true. So this is a valid argument. Let's look at 2. All baseball players are athletes. All ballet dancers are athletes. Therefore, no baseball players are ballet dancers. So let's see if we can draw this. All baseball players are athletes. So I have baseball players and athletes. I also have all ballet dancers are athletes. Okay, so I have both of these are true. I have baseball completely inside athletes and ballet dancers completely inside athletes. Therefore, no baseball players are ballet dancers. But you can see here, I can draw it where there are some baseball players that are also ballet dancers. So this proves a counterexample. So my argument is invalid for this one. All right, here's our next one. All mathematicians are logical. No poets are logical. Therefore, no poets are mathematicians. I want you to try to draw an Euler diagram for this one and then determine if the argument is valid or invalid. Okay, we have all mathematicians are logical. And we have no poets are logical. Therefore, no poets are mathematicians. So in this case, mathematicians are logical. Mathematicians has to be completely inside logical. Poets, no poets are logical, so that's completely separate. Therefore, no poets are mathematicians. That one is a valid argument. Let's try the next one. All mathematicians are logical. No poets are mathematicians. Therefore, no poets are logical. Please try this one and determine if it is a valid or invalid argument. Okay, so we have all mathematicians are logical. So again, we have mathematicians completely inside logical. Then we have no poets are mathematicians. So I can draw like this. So no poets are mathematicians. There's no overlap there. Therefore, no poets are logical. But we can see I can draw the picture this way where there are some poets that are logical. So this one is an invalid argument because we were able to draw a counterexample. Let's try number 5. All mathematicians are logical. Some poets are logical. Therefore, some poets are mathematicians. So take a minute and try to determine if this one is valid or invalid. Okay, all mathematicians are logical. We're starting the same way. We have some poets are logical. So I can draw a picture here with some poets overlapping with logical. Therefore, some poets are mathematicians. Well, here I have some poets are logical, but the poets do not overlap with mathematicians. So again, these two premises are true, but our conclusion is not. This is a counterexample again. So this argument is invalid. We have one last example. This one says, all mathematicians are logical. Euclid was logical. Therefore, Euclid was a mathematician. Try to determine if this argument is valid or invalid. Okay, we have all mathematicians are logical. Now we have Euclid was logical. Euclid is one person, so I am just going to make a little square, or you can make a little star. This represents Euclid. So both of our premises are true. Therefore, Euclid was a mathematician. Well, we can draw Euclid here within logical, but not within mathematician. And so this one, again, is a counterexample. So this argument is invalid. And that's the end of chapter 3.